Yes, sir. 10 minutes break are over.
Yeah.
Uh, I request all the participants to again focus on for the next section. Yes, sir. We'll start with the next session.
Okay. I am ready. Huh. Thanks to everyone once again. The previous talk was essentially based on the slides from Prakash Mughali. That was a very high level overview of the subject. What I'm going to talk to you now is something slightly different at the atomic or the molecular level with some applications. Okay. Now, at the outset, I must tell you that I am sure that the audience that we have here today are all with different backgrounds. Okay. Some would be working on mechanical properties, some would be working on electrical properties. The specialization subjects will be varied from person to person. And this trend of research work or knowledge is becoming more and more interdisciplinary by nature for any subject. Okay. So we need to understand not only where the subject in which we specialize, but we also need to see what exactly are happening in some other fields which can be applied to our area. And microwave technique or technology is one such thing which can be applied to many disciplines. Therefore, a knowledge of that will be very helpful either now or in future for most of you. Especially considering the factor that this is a very unconventional way of processing of materials with lots of advantages and hardly any limitations. So this particular talk now will be my own, and as in the earlier lecture, there could be some little bit of repetitions, but I will again pause now and then and seek questions from you so that the concepts become clear then and there. So what I'm going to talk about is again some introduction. Then we are talking about some mechanism called as the polarization. Then some functional materials or examples. And we take some examples as specific examples and then highlight how the microwave processing helps in preparing or manufacturing specific materials to our advantage. Um, all of you are aware that most materials can be classified as metal, semiconductors, and insulators. Okay, typical metals are copper, silver, gold, aluminum, steel, brass, zinc, and so on and so forth. The semiconductors are basically used in electronic applications like silicon, cadmium telluride, gallium arsenide, indium antimonide, so on and so forth. What is called as the 3,5 compounds or the 2,6 compounds are based on periodic table. Of course, silicon is still the workhorse of semiconductors, and this technology is India is lagging behind, and now government is giving a lot of impetus for the growth of semiconductor materials. Having said that, I would say that in general, the field of materials development is lacking, very much lacking in India. The reason for that being two or three things. One is we do not have proper expertise available in abundance. Second thing is the return on investment of working on developing new materials is usually very slow, not only in our country, but also in many other countries. It takes several years to develop a new technique or a new material. And third thing is that the proper development of a new material or an innovative material requires a lot of infrastructure facilities like testing and characterization methods, which are very, very expensive. And many institutions do not have access to such facilities. Therefore, by and large, the growth of materials technology in India is lacking. And the subject of insulators that is there in the blue in the right hand side corner is also known as dielectrics, because they are the materials which are insulators. They normally do not conduct electricity, nor they conduct heat very well. Such materials are called as insulating materials. And broadly speaking, the classification can be done based on what is known as the band gap or the energy bands. In the case of the metals, the valence band is full of electrons, but the conduction band is partially filled with electrons. So therefore, these conduction band electrons contribute to the electrical conductivity as well as to the thermal conductivity. In the case of semiconductors, the band gap is very small. So by doping or with any other activation, the electrons in the valence band can be made to jump into the conduction band, which can contribute to the flow of current. In the case of in the case of insulator materials, the band gap is very large, typically of the order of 4, 5, 6 electron volts. Therefore, there are hardly any electrons in the conduction band, and the electrons in the valence band are completely bound, so they are not easy to move. Now, let us consider a concept called as now I am going into the finer details of the microwave processing of materials. This requires, I am not going to use very complex equations, but that is not the required for this particular type of talks. And but some knowledge of the basic principles involved will be very helpful. As I mentioned earlier, that the talk will be relatively at the elementary level, because we have a mixed audience, or at least I assume that there is a mixed audience, and people in some other discipline may not be familiar with some of these things. So I keep it very simple. If it looks very, very simple to many of you, please bear with me. It is for the benefit of other persons who are not familiar with the area. Now, a dipole is nothing but a charge with some separated by a positive side and a negative side. In a system, overall, there is a charge neutrality is there. In this irregularly shaped article, there is a lot of negative and positive charges. Overall, it is charge neutral. That means equal number of negative charges are there compared to the positive charges. However, in some specific area, the charges are separated from each other, and therefore that we call as a dipole. Okay, the dipole moment is basically the charge multiplied by the distance. Okay, so in a system there will not be just one electron or one proton like that. There will be hundreds of thousands of electrons and protons. So when all those things are added, when you do the sum, then you have a total dipole moment for the system, which is a summation of the individual dipole moments. Okay, this concept of dipole is extremely important in understanding the interaction of microwave with materials. Now, let us take the example of a simple atom. Let us say hydrogen. There is a proton that is present at the center with a positive charge, and in the language of the physics, there is one electron going around the proton. Okay, I hope that all of you are familiar with that. From a chemistry point of view, this electron is not considered as a particle going around. It is considered as a electron cloud, which is given inside. Okay, so the net charge is 0 because there is one proton and one electron. So the total thing is 0. Now, let us consider this chemical view of the atomic hydrogen with one proton and one electron. So when it is by itself, there is no dipole moment because the center of the electronic cloud merges with that of the proton by symmetry, and so the distance between the charge separation is 0. Therefore, there is no dipole moment. Is this clear? Hello? Hello?
Yeah, sir, I think they need one more time. You can one more time repeat this this portion.
Okay.
Dipole path.
Okay. Let us consider a simple hydrogen atom. Okay. There is a proton. Hydrogen is one proton only present and one electron. Okay. So normally in the physics point of view, we say that the proton is at the center and the electron is going around the proton. Okay, circling like a particle. Electron we view it as a particle. Okay, but in chemistry language, that electron we consider it as a cloud, like a very thin cotton type of thing material, hazy thing which envelops the complete area of the atom. Okay, this whole area is with cloud of electronic charge distribution is there, and in this particular case, the center of all the electronic cloud is exactly at the center, so there is no separation of the proton and the electronic center of the electronic cloud. So the dipole is in this particular case is 0. The other way of looking at is, okay, the other way of looking at this cloud is, let us say at one point the electron is here as shown, this where my arrow is there. Okay, so the dipole moment is working like this, and some other point when the electron comes here, it is working like this, so it gets cancelled out. So time average over a period of time, the dipole moment is 0. Correct? As I mentioned earlier, the dipole means the charge multiplied by the distance of separation. So in this particular case, whether in this case or in this case, time average over some particular time, the net dipole moment would be 0, because at one point the electron will be here. Since it is going around, at some other point it will come here. So the dipole moment of when it was here and it was there gets cancelled out. Similarly, for each point on the diametrically opposite side. Okay. So net dipole moment for this hydrogen atom is 0. Okay. Now let us put this hydrogen atom in an electric field, which is going from this side to this side. Okay. So what happens is the electric field, this electric field, what happens, distorts the orbit. What it was circular earlier becomes like an ellipse, because the proton will get pulled on this side and the electron will get pulled on this side in an electric field. And now what happens is the center of the electronic cloud and the positive charge are not at the same place, they are separated. Therefore, now under the influence of an electric field, this atom of hydrogen becomes what we call as polarized. Okay, so now there is this elliptical orbit becomes such that the center of this electron is different from that of the proton, so there is a separation is obtained. Because, let me put it in a slightly different way, when the electron is here, let us assume the physics model, when the electron is here, the dipole is like this. But the same electron, when it comes here, because it is going around, the distance is only this much. So there is a net dipole moment created under the influence of an electric field. Okay. So therefore, we say that this electron has undergone a polarization and has created a dipole under the influence of an electric field. Am I clear?
Yeah, clear, sir.
Okay. So if I apply more electric field, let's say if I continue to apply a higher electric field, this ellipse becomes more flatter and flatter. The separation between the center of the electronic cloud or the electron and that of the proton increases, because this becomes more like a much more flatter. Okay, the large axis of the ellipse becomes much bigger and the short axis becomes smaller under the influence of more and more electric field. Therefore, the electric field has created a dipole out of the hydrogen atom. Originally, in absence of electric field, there was no dipole because it was center of the electron cloud and the proton was at the same place. There was no separation, so it was zero. But now, under the influence of the electric field, it gets distorted. The proton will have a tendency to go in this direction. The electron will have a tendency to go in the opposite direction. So there is a charge separation creating the dipole. Okay. And as you can see, the higher the electric field, more the separation is. So this we call as a induced dipole. Okay. Originally it was not there, but because of the electric field, we have created a dipole. Okay. So this ability to polarize or create a dipole is called as a polarizability, and obviously the induced dipole moment is equal to some parameter called as alpha E and electric field. As I mentioned earlier, as the electric field increases, the dipole total amount of dipole moment also increases, and that proportionality constant is called as a polarizability. Okay. So when you have a high polarizability, then the dipole moment will be very large, and also when the electric field increases, the polarizability, the induced moment, dipole moment, total amount of dipole moment also increases. Okay. So typically you will not be dealing only with one hydrogen atom. Okay, there will be hundreds of thousands of millions of hydrogen atoms will be there. Okay, and therefore there will be a separation of the electronic cloud to one side and the protons to the other side. Because the electron is very light compared to that of proton, the displacement of the proton is very less. However, the displacement of the electron will be much more. Okay. Now, this polarizability is function of many things, especially on the size. The helium is next to hydrogen is helium. It is very small, but as the argon and the atom becomes bigger and bigger, the polarizability increases. Okay. Similarly, lithium is very small compared to that of sodium. Sodium is small compared to that of potassium. Therefore, as the size of the atom or the ion increases, the alpha E, the polarizability increases. Okay. Same is the case with fluorine and chlorine. Chemically they are very similar. Chlorine is very big compared to fluorine. Therefore, the smaller fluorine has got lesser alpha compared to that of chlorine. Okay. So we can say that as the size of the atom or the molecule in general becomes larger and larger, the electronic polarizability increases. Okay. Because when the atom becomes bigger, the outermost electron has a tendency to get distorted very easily compared to a tightly bound electron when the atom size is very small. Now, earlier we talked about atom only. Now let us look at some compound like HCl or CCl4. Okay. Now, having the same concept, when we put the molecule of HCl in an electric field, not only there is a polarization of the electronic cloud and the proton, but the molecule itself will get displaced. If I consider HCl as H plus and Cl minus, okay, when you put this molecule in the electric field, the hydrogen goes in one direction and the chlorine goes in the other direction, and therefore there is a dipole created. Same thing happens in CCl4 and other things. Okay, there is a atomic or the ionic polarization. Earlier it was mostly electronic polarization. Now we are looking at the whole molecule or a atom itself, okay, shifting the positions. And this is known as the atomic or the ionic polarization. Then we have called as certain group of compounds called as polar compounds. Polar compounds are nothing but the whole material is electrically neutral, but in a small section it has got a positive and a minus sign. Okay, there is a dipole moment within the system. Okay, these dipoles under normal circumstances are very randomly oriented. Therefore, the total dipole moment available will be zero, actually, because for everything oriented in one direction, there will be something else oriented in the opposite direction. Therefore, the total net dipole moment in a system will be zero. However, under the influence of an electric field, these molecules or systems will have a tendency to orient towards the electric field. So when I apply an electric field from this direction to this direction, all the negative things will try to align in this direction, whereas the positive charges in the dipole moment will be in this direction. Okay, again there will be called as a polarization. This is known as a orientational polarization. Now, if the electric field is not very high, it is only less, then what happens is it may not completely align, it will be still be oriented in the towards the electric field only, but not fully. Let us take an example to understand this. Let us consider water molecule. Okay, water is called as a polar liquid for the following reason. Water is H2O. The angle between these two H is something like 107 or something like that. Okay, so if I look at the oxygen and the hydrogen, there is a force going from hydrogen to oxygen, because this hydrogen and oxygen are separated by positive and negative. Okay, so there is an electric field going from hydrogen to oxygen in this direction, in the blue direction. Okay, similarly, between this hydrogen and this hydrogen, the electric field is in this direction. I'm talking about the attraction, law of attraction. So when you sum these two things, okay, this one will get into vertical direction and the horizontal direction. This one also will be in the vertical direction and the horizontal direction. The horizontal ones will get cancelled, and there is a net dipole moment which is always present in a water molecule. If I look at just one water molecule, there is always a dipole moment associated with it. Okay, it is given here, and so I can represent water molecule, one water molecule, by a dipole like this. A negative charge and a positive charge separated by some distance. But what happens in regular, if you take a glass of beaker of glass of water, all these dipoles are oriented randomly, but the net dipole is zero, because for every dipole oriented in one direction, there will always be some other dipole oriented exactly in the opposite direction. So the net effect will be zero. But however, under the influence of an electric field, all these dipoles tend to orient themselves in the direction of the field, and hence it becomes polarized. This is what the meaning of polarized is. Now, this introduces to a concept called as the polar or non-polar liquids or solids. If you like, look at carbon dioxide or carbon tetrachloride, they are all very symmetric. The dipole moments, polar, this thing is zero, because for everything positive, there is a negative there, that it gets cancelled out. Whereas for the samples like water, which is asymmetric, there is always a permanent dipole moment, and such materials are called as polar compounds. Okay, it is this not only water, it is there in methyl chloride, ammonia, hydrochloric acid, etc., etc. Okay, all these things are polar. CCl4 is not polar, carbon dioxide is not polar. When I say carbon dioxide, you should take it as a gas only. Any question on this? So basically, what happens is that we have three types of polarization mechanisms available to us. One is because of the electronic polarization. The second one is ionic or atomic polarization. And third one is the orientational polarization. Orientational polarization comes because of polar liquids where the molecules are asymmetric in nature, as in water. Okay. Therefore, the total polarizability of a material is the summation of the electronic, atomic, and the orientational polarization. So when you add all these things, you get the total polarization of the material. Now, this total polarization is dependent on many things. One is definitely the temperature, because at different temperatures, the polarizability changes, and also at different frequencies. So far, we have talked only about static electric field. Okay. So let us talk about what happens when a high electric field, these polar compounds align completely in this particular direction. Now let us see if there is a molecule like this, let us say, okay, and it is a polar thing, and now I apply, instead of a DC field, I apply a AC field. Okay, that means it becomes oscillating. What happens is this dipole keeps changing the position like an oscillating, like a pendulum. Okay, it goes from one side to another side depending upon the electric field. Is this clear? When I apply an electric field, so at one time it is the electric field is in this direction, and after some time, because it is oscillating electric field, it becomes the opposite direction. So the dipoles will be swinging from one direction to another direction. Okay. Now, as long as the frequency is very small, these dipoles will be oscillating in resonance with that of the electric field. Okay, let us say in kilohertz. Okay, so in kilohertz, as the electric field is oscillating, the dipoles also will match that of the electric field of the oscillating electric field. Okay, but as the frequency increases, the rapidness with which the dipole can oscillate will find it more and more difficult, and at some level it cannot match that of the oscillating field, as in gigahertz. Okay, in gigahertz the electric field is changing extremely fast. Okay, and these molecules cannot match with that of the electric field, and therefore there is a lag created between the oscillation of the dipoles and that of the electric field, and this creates friction, and this is the one that causes heating of the material. This is the principle of the microwave heating of materials. Understanding this is very important, and therefore I am kind of stopping for a moment. If you have not understood, let me repeat it again. Hello?
Yeah, sir. I think all are okay with this.
Okay.
It
So
is pretty.
basically what happens is these dipoles that are present in any liquid, solid, or a gas, okay, at low frequencies can align themselves as per the applied electric field, oscillating electric field. Okay. But as the frequency of the electric field increases, it cannot match. Okay. And therefore there is it will lag behind, up to some level it can match, join along with that of the applied oscillating electric field, but after very high frequencies it cannot. Therefore, it's kind of a lagging behind takes place, which creates friction, and therefore the sample will get heated. This is the principle of microwave heating. Now, there are three important parameters that can be characterized for any material electromagnetically. One is called the dielectric constant, which is basically the capacity of the material to store charges, okay? And the other one is the dielectric loss, denoted by epsilon double prime, which is the capability for the conversion of the material to get heated up, okay? This is a dielectric loss. The loss happens because of the mismatch between the applied electric field and the dipole moments that are present in the material. And the tangent loss is denoted by something called the tan delta, which is nothing but the ratio of epsilon double prime and epsilon prime. That means capability for absorption and convert stored energy into heat, okay? So for any material, when you want to apply microwave furnace or a microwave oven, you need to kind of get an estimate of whether what exactly is the dielectric constant epsilon prime and the dielectric loss denoted by epsilon double prime, okay? And these two parameters depend upon the frequency as well as the temperature, okay? Let us look at some values, okay? Let us look at water. Water has a epsilon prime of 78, which is very high, and an epsilon prime of double prime of 12, which is also very high, okay? So therefore, water is a very good absorber of microwave energy. The reason for that is water is a polar liquid, okay? It has got a orientational dipoles already present. Therefore, it can oscillate under the influence of an electric field. Therefore, at very high frequencies, it becomes an absorber. Now, if you look at Teflon, which is a plastic material, the epsilon double prime is very, very low. It hardly kind of interacts with the microwave. Therefore, you can very safely use Teflon material in a microwave oven because it will not get absorbed any heat. It will not, nothing will happen to the Teflon. It becomes transparent, okay? If you look at alumina, okay, again, epsilon double prime is very low, 0.009, and therefore alumina is transparent to microwave at room temperature of 25 degrees centigrade for 2.45 gigahertz. See, when I put the values of epsilon prime and epsilon double prime, it is always with respect to a particular temperature and a particular frequency. At some other frequencies, the values can change, okay? Since we are interested in microwave drying and heating, we are focusing on values of the frequency always at 2.45 gigahertz. And because some calculations, people have found out the total amount of heat energy that generates when you apply a microwave onto a substance depends on the frequency F. In our case, it is 2.45 gigahertz. Epsilon double prime, which is basically the column here, and the electric field square, which is basically the power of the magnetron, okay? Now, you know that in the magnetron, the power you can adjust it as per your need, okay? Not in a kitchen microwave oven, but in an industrial microwave oven, we can smoothly increase the power from 0 to 100% to whatever value that you want, okay? But this is not possible in a kitchen microwave oven, okay? So therefore, you can estimate whether the material will get heated or not under a microwave, knowing the dielectric parameters of epsilon double prime easily, okay? Now, if I look at dry sand, the value is 0.11 epsilon double prime. Therefore, people who use sand in foundry applications, they make what is called as a core, okay? So the sand will absorb the microwave, and hence the core can be dried, which has got moisture, using microwave. And this is one of the novel applications of microwave in a foundry industry. Let me spend some time on this. In a foundry, they make a mold, typically with that of sand, right? I think they use some sodium silicate or ethyl silicate or some binder, and make an object which is inverse to that of the parts that you want. And some of these things are very big, typically of the order of 1 foot or 2 feet or 3 feet, like a automobile engine and things like that. Okay. These sand cores are very big, and when you want to dry it, it has got moisture during fabrication. So when you want to dry it, you cannot heat it very quickly to 110 degrees centigrade to remove the moisture, because then it will crack. Okay. So it has to be done very, very slowly, and typically over 1 day, 2 days, like 3 days it will take when you have a large dry sand core. Okay. But with microwave, because it penetrates into the deep into the material, and also it gives rise to uniform heating, the whole thing can be done in less than 30 minutes or 45 minutes. What takes 2 to 3 days can be dried within 1 hour or half an hour, depending upon the size of the core. Is this application make sense to you? Because removal of moisture is also not easy. In a conventional way, it has to be done very slowly. If you do it very fast, then what happens is the surface, the water comes out very quickly, whereas there is still plenty of moisture inside. And once the surface water comes out, the matter there shrinks, and that creates mechanical stresses, and the sample will break. So in order to avoid that, what people normally do is they increase the temperature by 1 degree for 3 hours, like that. Very slowly they will increase the temperature, so that differential temperature is minimal, but then it takes 2 to 3 days to dry it. But with microwave, the whole thing can be done very fast, because the surface as well as the inside are dried at the same rate. So the important thing is the total amount of energy that is available as heat is basically depends on the frequency, the epsilon double prime, which is basically the loss material, and the electric field. So this table gives you the values for different materials at room temperature for various materials. Okay. Now, if you see, for example, unfortunately, it is not here. In a kitchen microwave, you have a glass right at the bottom, which is a turntable type of thing that is made of fused silica. Okay, it is a special type of glass, and it doesn't absorb any microwave energy. Therefore, it can be used very safely, and keep your other materials like cups and saucers on top of that. So obviously, you see, if you have a material like a methanol or an ethanol, you should not put it in a microwave oven, because the dielectric loss is very, very high. Okay, and they are also combustible materials. So if you are putting them inside a microwave oven and switch it on, the chances of an explosion is very high. You look at the last row, aluminum oxide, which is a workhorse of ceramic materials. The epsilon double prime, which is a dielectric loss constant, is very low, 0.0063. And therefore, we say that the aluminum oxide doesn't absorb microwave easily. So is the case with magnesium oxide. They are all transparent to microwave oven. But this is only at room temperature. But as the temperature increases, we will see that part later. The epsilon double prime increases. Therefore, at higher elevated temperatures, it will start interacting with the microwave. Any questions, sir? There is none. Let me proceed. Let me take some specific example to highlight the application of this technology to make real materials. Okay, you're all familiar with tungsten carbide. At least some of you will be familiar with tungsten carbide. It is a very strong cutting tool material, very widely used in industries to cut metals and other things because it's a very hard material. The melting point of tungsten carbide is very high. I don't know, 2000 degrees or more, or I don't know, something like that. Very, very high. So normally it is extremely difficult to sinter that material by powder metallurgy technique. So what people do is they put a little bit of cobalt into the tungsten carbide composition, and this cobalt melts and forms an interface layer, and therefore the sintering takes place at a relatively low temperature of 1450 degrees centigrade. Okay, 1450 degrees centigrade for tungsten carbide is, I would say, is a relatively low temperature, and the total cycle time, depending upon the size of the component, can be anywhere from 12 to 24 hours. Let's say one day. Okay, so you start the furnace today morning, and the next day, tomorrow morning, we come out and you will be able to open the furnace. Okay, then there is something called as the soaking time. Can somebody tell me what is soaking time? Are you familiar with this word soaking time?
I'll just remove the mute restriction, sir. We had put the mute restriction. Just a second, sir.
Yeah.
That's why people were not able to ask the questions.
Oh, okay. I'm sorry.
Yeah, now the restriction has been removed, sir. I can ask the question.
Yeah. Does anyone know what is soaking time?
Sir, it is duration of material at its peak sintering temperature, sir.
Exactly. Very good. Very good. Okay. So in this particular case, if the sintering temperature, maximum temperature is 1450 degrees centigrade, so soaking time means we reach 1450 degrees centigrade and keep it for 60 minutes. Okay. That is called the soaking period. Okay. Soaking time. And in this case, it is 60 minutes. And the density that we get is of the order of 99.7, provided we use cobalt as the one of the material inside, because it's a composite of tungsten carbide and cobalt. Okay, the higher the density, the better the properties of the tungsten carbide tool. Okay, the average grain size that we talked about, okay, when seen under a microscope, is typically is of the order of 2 micrometer. What it means is the starting material of the tungsten carbide should be very, very fine, and then maybe submicron, then it becomes about 2 microns. So then we have a bending strength and the hardness. Okay. Suppose I use microwave for sintering this material, then the sintering temperature can be brought down from 1450 degrees to 1300 degrees centigrade. Okay. A difference of 150 degrees centigrade. Okay. Now, you may say, oh, what is there 150 degrees centigrade out of 1300? What is the big deal? No, it has got a lot of implications, because as you go to higher temperatures, the cost of power increases tremendously. Okay, going from 300 degrees to 400 degrees, maybe 100 degrees centigrade difference, the cost may be something, but going from 1300 to 1400, again 100 degree difference, the cost will be many, many times more. As you go to higher and higher temperatures, the cost is very high. Secondly, as you go to a higher temperature, the kind of refractories that are used in the furnace will be of a different nature. Okay, it becomes costlier, and therefore the overall cost increases. Now look at the cycle time. With the microwave, it is only 90 minutes. What was taking 24 hours or overnight is reduced to 1.5 hours. Okay, soaking time is only 10 minutes rather than 60 minutes. And you can, the reason cycle time is so low is because you can go to a very high temperature very quickly, because the microwave power can increase very quickly, and theoretical density is also more. Average grain size has reduced from 2 to 0.6. Okay, a tremendous advantage, because as you reduce the grain size, the mechanical strength properties and the hardness and other things improves dramatically. The bending strength has improved and the hardness also has improved. Okay, this is the power of microwave sintering. You please stare at it and see the difference. Now, if somebody is manufacturing tungsten carbide with a conventional technique, and a competitor comes with a microwave sintering, what he can do in one day, this fellow will be able to do 8 times more than that. Okay, the productivity, throughput, everything increases tremendously, and this fellow's product will be much, much superior. Any comments?
Beautifully explained, sir. I think this is much more convincing.
Yes.
Any participants, I think they have to say? Okay. The slide is like totally blown off the minds.
Yes. I mean, this is the power of microwave. Okay. Now let me see conventional densification of alumina. As I mentioned earlier, aluminum oxide is the workhorse of ceramic industry. Most generally used products with ceramic materials invariably will have different percentage of aluminum oxide. If you look at the catalog of aluminum components manufacturing company, it will be 60-70 pages actually, with the different compositions, different amount of aluminum oxide, so on and so forth. Okay. Aluminum oxide nowadays actually it is a white material. Okay. But when you sinter it fully in a proper way, you can make it transparent. Aluminum oxide, the band gap is, I don't know, 5 electron volt or 6 electron volt. It is a very good insulating material. So if you densify it fully and properly, it can be made transparent. And such type of things are used in space applications for a mirror and things like that. Okay. Now let us look at the sintering of aluminum oxide with conventional sintering and microwave sintering. Okay. We talked about this in the previous talk. Basically, you start with a very sub-micron size aluminum oxide powder. Okay, sub-micron means the average particle size would be of the order of 0.5 or 0.6 micrometers. And it will have some 0.25% of magnesium oxide, which is used as a grain growth inhibitor. Okay, you mix it with little bit of water, typically 2%, 3%, little bit of polyvinyl alcohol as a green binder, and also maybe CMC, some wax, things like that, and mix it very nicely. And this powder, you fill it in a die cavity and press it. Okay, and when you press it, the density will be approximately 55% of the density of the alumina. Alumina density is about 3.97 or something like that. Let's take it as 4. So 55% of it means you will get a green density of something like 2.4 or 2.5 grams per cc. Okay. And then when you start heating it, first the water goes and then the binders goes at about 400 degrees centigrade. All the CMC, PVA and all those things are gone. And then when you continue further, as I mentioned earlier, at about 1200 degrees centigrade onwards, as you increase it, okay, the diffusion of aluminum oxide, aluminum takes place, and the particles of aluminum oxide tend to coalesce with each other. They tend to join together and become bigger and bigger. Okay, what was 0.6 becomes 1, and 1 to 1.4, 1.5, like that it becomes. Okay, but it has to be done very slowly, because the furnace, first of all, cannot go to normal. In a conventional furnace, you cannot go to a very high temperature very quickly. It has to be done very slowly, because if you heat it very fast, even the insulation bricks will crack because of what is called as a thermal shock. Okay, it has to be done very slowly, and also the sample also has to be heated very slowly, because you don't want too much of a differential thermal gradient at the center of the sample and the surface of the sample, which is exposed to the heating elements. Okay. So typically, depending upon the size of the sample, it will be for 1 to 2 hours. Okay, this is where the soaking takes place. Okay, this is where the soaking at the top. Okay, typically 1 to 2 hours is the soaking period. Okay, then you get about 99 or 99.5% theoretical density. The balance being pores, either it will be open pores or closed pores. Okay, But when you do it with microwave, okay, you get much higher when you get much higher density very quickly, because it starts sintering very quickly, because you are able to heat the sample very quickly, one thing, and secondly, the samples become very reactive even at much lower temperatures. Okay, so and the full theoretical density, you don't have to go up to 1600 degrees centigrade, you can reach even at 1400 or 1450. Okay, so again there is a difference of about 150 to 200 degrees centigrade between the conventional heating and the microwave heating. First point is that maximum temperature required is reduced. Second thing is you are able to achieve it at much lesser time. Third thing is the lesser grain growth, therefore the product that you get is much superior to that of the conventional heating. Now, this alumina heating by microwave cannot be only by microwave only, because of the graph that I am showing here. Let us look at 99% aluminum oxide. Okay, if you see the tan delta, which is basically a representation of epsilon double prime by epsilon prime, which is very low till about 600 degrees centigrade, right? You see the graph here at the bottommost graph, okay, line in the graph. Up to 600 degrees centigrade, it hardly absorbs any microwave radiation. Therefore, either you use a hybrid technique, that is use infrared heating or some resistance heating to heat the sample to 600 degrees centigrade and then apply the microwave field, or you apply what is called as a susceptor. That means you keep some silicon carbide around the sample so that the silicon carbide absorbs even at much lower temperatures, heats up the aluminum oxide to 600 degrees centigrade, and then the alumina starts absorbing. Okay, and this is the reason why you need to understand the electromagnetic properties of the material while dealing with microwave. Compared to 99% alumina, if you look at the 97% alumina, it has got some other components, the 2%, that has got a better microwave interaction even at lower temperature. Okay, so depending upon the composition, the interaction temperature varies. Then there is another class of material called as transparent ceramic materials. These are used in very corrosive atmospheres. Like for example, when you are heating something to 2000 degrees centigrade and you need a window to observe what is happening inside the furnace, or in some space application and things like that, you need a transparent ceramic materials. Typically, these things are normally done in the past using a technique called as hot pressing. Okay, what it means is that you press the material to a very high pressure, and then at that pressure only you increase the temperature to very high temperature. Therefore, the porosity is completely eliminated and the sample becomes transparent. Sometimes it is translucent. It may not become completely transparent, but it can become translucent. Okay, so in such applications, the grain sizes are very, very small, and density is much better. Only thing is, this cannot be done on certain complex crystal structure like monoclinic. It is applicable for cubic and hexagonal and tetragonal and like that. If it is monoclinic, because of the asymmetric nature of the grain growth and things like that, this becomes very difficult to get transparent ceramics for monoclinic systems. Porosity is very low, impurities are the lowest, and sometimes there are some liquid phase sintering is used and grain boundary phase which is formed, and that can also be reduced very much. Now, I talked about the microstructure of a typical ceramic material. If you look under a microscope, it will be like this. It will not be, when you say average grain size, it is not just all the grain size of the same size. It will all be different. The bar here, the white line, shows it is about 5 microns. Okay, so just by looking at it, some are, this one is maybe 5 grams and this one is very small. But what they do is the average grain size is what they calculate, And in this particular case, probably the average grain size is about 3.5 or 4 micrometer, which is good but not great. Okay, and you will see some small dark spots here. There are all some pores. Okay, in this particular case, when the grains are merging with each other, somehow there is a little pore that is formed. Okay, any question on this? Let me take one more example, which is called as the barium titanate, which is a capacitor material. All along we have been talking about epsilon prime of 5, 6, 7, 10 like that. Water of course is about 78 or 70, 80. Okay. When there is a class of material called as titanates, okay, what is known as a perovskite structure. This material can have an epsilon prime of 7,000, 8,000, 9,000, even 10,000. Okay, extraordinary capability to store charges. Therefore, it is a wonderful capacitor material. Okay, so when you have material of epsilon prime of that number, what it means is that the capacitor size can be very much reduced and therefore can be used in integrated circuits, miniaturization of the capacitor. Okay. Now this material barium titanate, if you look at about in the 1970s, okay, lot of people used to work on this particular material, and this material is it has got a structure like this. The titanium ion is at the center of a cube, okay. Then the oxygens are there like an octahedral on the faces of the cube, and the corners of the cube are filled with a large barium ions or atoms. Okay, so barium is very big. Titanium is actually very small. It is but though it's shown big here, it is normally very small, and so is oxygen. Okay, so this is the structure, and this is the cubic structure above 130 degrees centigrade. Okay, this material above 130 degrees centigrade, the structure is like this. Okay, now when you bring the temperature to temperatures below 130 degrees centigrade, or let's say even at room temperature, what happens is this cubic side means all of them are equal, but below 130 degrees centigrade this becomes tetragonal. That means the z direction is increased compared to the x direction and the y direction. Okay, and this change in the phase or the structure of the material makes it tetragonal, and therefore it induces dipole moments. It becomes like a polar material now. Okay, it is an intrinsically a polar material because the z direction becomes more than the x and the y direction. Okay, and this material is of tremendous interest to miniaturization of electronics. Okay, and so this material is shown as a function of dielectric constant of this material is shown as a function of temperature. So when you see that 120 degrees centigrade, 130 degrees centigrade, the epsilon double prime goes to very high and then drops down, but at much lower temperatures, the dielectric loss is also very low. Now, this material has tremendous interest, and now this material can be done by microwave technique at a temperature as low as 700 degrees centigrade compared to 1300 degrees centigrade. Okay, the conventional method way is you start with barium carbonate and titanium dioxide, mix them together and heat it very slowly to about 1300 degrees centigrade, and again for 2-3 hours like that, and invariably you don't get very good barium titanium. There is always some other compounds of barium and titanium present in the material. Okay, and that deteriorates the electromagnetic properties of this material. Okay, and as I said that in the 70s, hundreds of laboratories used to work on this material to develop a superior material. Now with microwave, they are able to do it at even at 700 degrees centigrade, the required tetragonal phase very easily in less than 15 minutes. What used to take 2-3 hours of soaking time at 1300 degrees centigrade can be done in 15 minutes at 700 degrees centigrade, because the titanium that is present interacts with the microwave very easily, and therefore the rate of reaction dramatically accelerates, forming the required tetragonal phase of barium titanate. Have you understood, or should I repeat it again? I would like to mention one thing that many of you may be knowing this. You see all the macroscopic parameters of any engineering material, like density, compressive strength, tensile strength, electrical conductivity, thermal conductivity, chemical properties, all those things we measure for engineering applications, right? But each and every one of those parameters are actually dependent on the atomic or the molecular properties of that particular material, like crystal structure, what is the composition, what are the electromagnetic properties like epsilon prime and epsilon double prime. All these things will determine the macroscopic properties. And a material scientist like me is the one who makes a correlation between the microscopic properties and the macroscopic properties. Okay, the macroscopic properties are all determined by the atoms and molecules, whether it is electrical conductivity or thermal conductivity or mechanical strength or whatever it is. Okay, so therefore, when you want to develop a supercapacitor material like barium titanate, you need to understand the crystal structure of the material, what happens to the material when you heat it to a high temperature, how the electromagnetic properties changes with the temperature, and all those things are to be seen. So obviously around 0 degrees centigrade there is a phase transformation that takes place. So above 130 degrees centigrade it is cubic, but below that it is tetragonal. So when it is tetragonal from about room temperature to 120 degrees centigrade, you look at the dielectric constant. It is 8,000, 9,000. It reaches the very, very high dielectric constant. That means that material can store enormous amount of charges. It's a supercapacitor material and therefore very thin sample of that can store a lot of charges and can be used in miniaturization of electronic systems. I am sure most of you are familiar with at least heard the graphene. If you have not heard, I think invariably this material is going to impact sooner or later most of your activities, whether it is a mechanical property, electrical property, thermal property, or any other property. Okay, this material is going to make a disruptive intervention in materials field for a wide range of system. Okay, this is the strongest material. This is the highest electrically conducting material. This is the highest thermally conducting material. Everything highest. Okay. So some of the properties that one talks about when deal with graphene is the following. I would like you to stare at this particular slide for 1 or 2 minutes. Okay. Any questions or clarifications? It need not be a question, it can be even a comment.
So one question from
Yeah,
here.
yeah,
The room, whoever is here, one of our PhD students.
yeah.
He wants to know about shed some light on thermal stability of graphene. Thermal stability of graphene.
Uh, I think it's a very stable material. Nothing happens to graphene even at elevated temperatures. Okay. And it has got one of the highest thermal conductivity. It is much better than diamond. If I remember correctly, copper has a very good thermal conductivity of 400 watts per meter Kelvin. Okay. Diamond has 2000 watts per meter Kelvin. That means it can diamond is 5 times more thermally conductive than copper. Okay. And graphene is much better than even diamond. And the stability of graphene is very good, at least up to about 500, 600 degrees centigrade in an oxidizing atmosphere. Okay. In a non-oxidizing atmosphere, probably it's stable even at much higher temperature.
Very, very valuable point, sir, because he's carrying out his research in graphene additions. So,
You are involved in that?
yeah, he's my student.
So what are you doing, please? Can you just can I comment a little bit more? If I can, tell me the system that you are using.
So he's using aluminum, but aluminum there is come from machining waste,
Okay.
particularly for your aerospace grade material.
Okay.
And he is working on formulations or adding mixtures, various mixtures of graphene added into your aluminum
Aluminium metal.
metal
Okay.
in chips form, machining chips form.
Okay. Okay.
That aluminum is not your CP commercially pure aluminum or one series or 1100.
Okay.
Maybe you have seven series and two series. Aerospace.
So when you are mixing and when you are sintering, right? You are sintering somewhere, right?
Yes, exactly.
You have to
Yeah.
ensure it is done in vacuum or under the atmosphere of argon or nitrogen.
Okay. Any specific reason, sir? Because you said 500 to 600 degrees
Yeah,
Celsius.
what happens is it is a carbon. After all, it is graphene is carbon. If it is around in presence of oxygen, it will become carbon dioxide. Even diamond becomes carbon dioxide at 600 degrees centigrade.
Okay.
Then you will have a very expensive, one of the most expensive carbon dioxide in the world. Same thing happens to graphene also under oxygen atmosphere. So you have to process your system in an initially maybe with nitrogen, if not argon, first vacuum and then nitrogen atmosphere at least. You have to evacuate it completely, remove all the oxygen as much as possible, flush it out with nitrogen or hydrogen is even better, and then melt your system, melt or do whatever, sintering or whatever you want to do out there. It cannot be done with oxygen atmosphere.
There are two questions here, sir.
Yeah.
Continuation of this. Suppose if the dosage of carbon in given aluminum is very less,
Yeah.
under that circumstances also the
Yes.
oxygen issue.
Yes. Because oxygen can interact or react with graphene. I think around any carbon material will react around 500, 600 degrees centigrade.
But if we are working at RT, without any control of the atmosphere in like regular atmosphere,
If you do it in air, what will happen is graphene will become graphene oxide. So advantage of graphene is lost.
even if the working temperatures are around 300, 350, 400 degrees.
Even then, I would say that slowly it will start oxidizing. It is a question of rate of reaction. Even at 300 degrees centigrade, I am sure the graphene will start reacting. May not be very high, but still it will become oxidized.
And second point is initially when we create vacuum and then go to purging of nitrogen or argon.
Yeah,
Uh, so
that
it,
helps. That
it
helps.
is it
Actually,
is said
best thing will be you evacuate it 2-3 times, purge it with nitrogen or hydrogen several times. Okay, and keep the hydrogen atmosphere even while you are doing your sintering or melting or whatever you are doing.
Okay.
So that you are absolutely sure that your graphene is not oxidized.
And like there is some limit of creation of vacuum levels, particularly in micro heating. Can you shed some light on that, like 100% vacuum or 80% vacuum?
See, the vacuum is measured in terms of torque, okay?
Yeah.
So either use a mechanical pump, which will give you about 10 power minus 2 or minus 3 at best, okay?
Yeah.
And otherwise, you have to use a other types of oil, I mean, what is it called? Other one, diffusion pump, which will give you 10 to the power minus 6 torque.
Because somewhere we read and we were trying to understand if vacuum is created, plasma creation will be there in microwave while heating.
Correct. So when all these issues will come up, okay. But my suggestion to you is at least 10 to the power minus 2 minus 3 torque. First you purge it several. I mean you create a vacuum, flush it out with hydrogen or nitrogen 1 or 2 times. Okay. Keep the gases flowing and then do your experiment.
Okay.
Instead of doing it in air. Yeah, atmosphere, normal atmosphere.
Okay. Okay. I think many things were clear, sir.
Yeah, okay.
Yeah. Yes, sir.
Just for your information, even diamond, which is a very hard material, if you heat it to 600 degrees centigrade in a normal atmosphere like with oxygen, it will become carbon dioxide.
Very, very good point.
Yeah.
Noted, sir.
Okay.
Yes, sir. You can continue, sir.
Continue? Okay. So now I'm going to conclude. Microwaves have many distinct advantages in the processing of materials, and there are very few limitations. There are hardly any limitation for the microwave. Everything is a plus, okay? Hardly any negative points. We have seen through examples of aluminum oxide, barium titanate, and other things that tungsten carbide and so on. We get much better products in terms of quality and at much lower cost. Lower cost because temperature is lowered, time is lowered, and power is lowered. Okay, so everything is an advantage. Then because we are using microwave, there is no emission of carbon dioxide and other things, which is normally done when you fire with oil fired or diesel fired and things like that. There are many people who still use these old techniques. When you use the microwave, the control of your temperature, profile, and other things can be much better because they are all electronically controlled, not mechanically controlled. And as you have seen in the case of barium titanate and other things, that one can get extraordinary properties with a better understanding of the interaction of microwave with advanced materials. And graphene is a very good example. We are making graphene in Enerzi microwave systems. And as I mentioned earlier, it takes hardly 2 or 3 minutes to go from room temperature to 1000 degrees centigrade, and which otherwise will take one whole day or at least one shift. Okay. And even if the shift is over by conventional furnace, you cannot open it at high temperature, so you have to come only next day. So cycle time is reduced from 1 day to 10 minutes. Okay. And now it is a proven technology. I mean, all types of people are using this for various applications. As I said, not only for materials, it is also used for sanitization of hospital waste. It should be used in sanitization of municipal waste also. It is used in food industry. Most of the foreign food company they sterilize the food items with microwave now. Earlier they were using some pesticides and other things. Now they have shifted to microwaves. So it's all a green go for microwave technology.
session is open for question answers.
Yes.
Before we go, I have one question from
Yeah.
my side. It's a very important thing. What I noticed here is of tan delta, tan alpha. How do you call it, sir? The
Yeah.
tangent.
Yeah. Tan delta. Yeah.
Tan delta. So tan delta, that is alpha prime by alpha double
No.
prime.
Epsilon double prime divided by epsilon prime.
Epsilon double prime divided by epsilon prime.
Yeah. Yeah.
So
Epsilon double prime relates to loss, heating, basically you can say heating, and epsilon prime relates to the storage of charges.
so here, like we have handbooks, ASKM handbooks and other
Yeah.
handbooks. We
Yeah.
get data for our mechanical behavior for different materials.
Yes.
So such things regarding tan delta and
Ah,
epsilon,
yeah.
where can we refer to?
Yeah. Yes. Very good question. Very good question. Is a very valid point also. Okay. So there is something called the MAT web.
Mat web.
MAT web. For
Uh,
any material, you will get the values of what is called the under dielectric properties. You get these values.
MATWEF, mat
Yeah,
web.
MATWEB.
AB.
Okay. This is, but then I must also caution you one thing.
Yeah.
See, the measurement of those parameters are done for a particular composition in a particular way. So all the values that you get, you should take it with a pinch of salt. I mean, it could be when you say that epsilon prime is 60, it could be 55 or it could be 65 also, because it depends upon the purity of the material, how it is, particle size of the material, grain size, and so many other parameters. Okay, but it gives an indication.
Yeah. So another continuation of this is
Yeah.
delta is calculated from epsilon double prime and epsilon prime. So out of epsilon prime and epsilon, two columns were there.
Yeah.
So it looked as if epsilon double prime was more significant, like it was affecting more compared to epsilon prime.
Can
The
you
value
repeat? Can you repeat that statement? Epsilon double prime is more.
more important or significant in
Yeah, for heating purpose, epsilon double prime is more important.
Yeah. So as the session is going on, now we are posting the feedback and attendance parallelly. So the participants can parallelly give the attendance as well as feedback in the chat box. In the same Google Meet link. We are not putting it in the WhatsApp group. We are putting it in the Meet link only, just to track. And we have kept a tracker here, wherein attendance can be tracked and of the participants, and the time can be tracked for which they were available.
Yeah. Before I conclude, I must inform all of you that if you have any other question later on any of the things that I talked about, you can contact me through your professors or directly also. You can share my email ID with any of your audience. Okay. And to the best of my knowledge, I will try to answer.
Still there are 1 minute or 2 minutes. If any participants want to ask
Yeah,
any
sure. No, I can go on for even 15 minutes. No, I don't have any problem.
I have one question, sir.
Yeah.
So basically, I'm not from the materials background.
Yeah.
I'm just curious if we try to sinter that sintering process for controlled composition of metal and ceramic. Is it possible?
Okay. Yes, it is possible. Yes. See, you are asking me a general question. My answer will be very general only.
Yes, sir.
If you talk about a very specific system, then I will be able to comment more.
Specifically, if we talk about aluminum and alumina.
Yes, you can make that type of composites. Yes, you can do it.
Okay. And the controlled, I'm trying to see that if you take the functionally graded material, it has controlled percentage over the thickness.
Yes.
So is it possible to get that percentage accurately?
Yes, yes, yes.
Okay.
See, it's all, you have to kind of plan your experiment in such a way that you get the best out of the system that what you are trying to do.
Mhm.
In general, it is possible.
Okay. Okay. Yes. Thank you very much.
Any other questions, please?
Sir, I have one question, sir.
Yeah.
Sir, what is meant by intrinsic mobility, sir?
Intrinsic mobility, in what system or what context you are asking this? Intrinsic mobility basically means, okay, the ease with which the charges in general, for example, electrons in a semiconductor moves under the influence of an electric field. See, the electrons in, let's take the system of a semiconducting material, right? Hello? Hello?
Yes, sir. Yes, sir. Yes, sir.
Let's take a semiconducting material, okay?
Yes, sir.
And let's say gallium arsenide, okay? It has got electrons and it has got holes, okay? Now, the mobility of these charge, the mobility of these things, the ease with which it can travel is the intrinsic mobility. But when you dope it with some other ingredients, like if you dope it gallium instead of boron and things like that, okay, then the
Yes, sir.
mobility
Yes.
is affected because it encounters these additional impurity sites or distortions in the crystal structure.
Yes, sir. Yes, sir. Concept is clear, sir.
Or if you dope, even if you like, for example, if you take silicon, for example, either for a P type you put boron,
Yes.
for N type you put phosphorus, typically, okay?
Yes, sir.
So in a pure silicon there will be some mobility for these holes and electrons. But when you dope it with lot of either boron or phosphorus, the mobility changes because it will interact with more. They bump into each other more often. Therefore, the mobility is affected.
Yes, sir.
Yeah.
Thank you, sir.
Yeah.
Any more questions, please?
Can you tell me how many people were there in the audience?
Right now, 102 are there, sir.
Okay, there's a century.
And,
Okay.
yeah.
That's a
And
long. Actually, I would prefer to talk live because then I can, interact with people more easily. But then I understand the distance and the cost of travel and other things. It doesn't make sense to organize. So this is okay. But as a speaker, face-to-face interaction is much better than through the live video call.
yeah, definitely we'll be arranging, sir, in future. Because excellent, whatever information you have given. At many places, it was like mind-blowing. Few slides.
Yeah. Okay.
Uh,
Thank you.
it will be helpful for all the researchers, particularly.
So
And many
as I mentioned that if any of you have got any other question, please write to me and I will try to answer.
so I think if any questions are not there,
Yeah.
I think we can conclude the session for
Yeah.
today. But from our team GITV and all the participants, to express heartfelt gratitude and thanks. It was both the sessions were excellent, sir. Both the sessions were very, very good, very good. No words to them.
Thank you to you. Thanks to Dr. Malik and thanks to all your audience. I enjoy interacting with everybody, and the questions were also meaningful. And thank you very much. Namaste. Good night.
Good night, sir. Good night. We request all the participants to uh, give the feedback, whatever link is posted in the chat box, and give your attendance over there. Okay. So it will be open for some more time and for another 5 minutes. So we
Okay.
can, yeah. Now we will close the session and we will meet for tomorrow's session sharp at 5:55. 5:55. Yeah.
Thank you.
Thanks a lot, sir. And thanks to all the participants for their patient listening and for the 100% attendance.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you very much.
Stop recording. Stop it.